Let's continue talking about functions. We're going to look at function notation. In fact, this came up when we were looking at appropriate domain, the word problems on Delta Math. So we probably should have discussed this first, but this will help fill in those blanks about function notation. At the top of the notes, it says, when referring to functions, especially if we're working with more than one function at a time, it can be confusing to distinguish among them because they all begin with y equals. Y equals this and y equals that. And if I'm working with multiple functions at the same time, if I'm trying to talk to you about the functions, it gets difficult. So that's where function notation comes in handy. It can help us distinguish between different functions by renaming them as like f of x or g of x or h of x. And you probably have seen f of x the most, but we can definitely name it using g, h, any other letter that we want to. Just f, g, and h are the most common. For instance, if I have the function y equals 9 minus 4x, I can rewrite that as f of x equals 9 minus 4x. All that I did was replace the y with f of x instead, but it's the same function, it's the same equation. I'm just renamed it instead f of x. Function notation is useful for evaluating as well, and this is what we saw on those appropriate domain word problems on Delta Math. They were using function notation as we tried different values for the input for the x values. For example, to evaluate f of x equals 9 minus 4x for x equals 2. When you want to substitute that 2 in for your variable, you can show that as f of 2 and then filling in your equation where you replaced x with 2. And then you can finish by showing someone, hey, f of 2 equaled 1. When I plugged in 2 for x, when it was f of 2, my output, my answer was 1. Or another example, like if I had plugged in 3, I could write f of 3. When I plug it into that function, 9 minus 4x, it equals negative 3. And so you could keep going. You could keep listing different inputs and your outputs, and then somebody could come and say, oh, when they plugged in 2, they got 1. When they plugged in 3, they got negative 3. And it's just much easier to see instead of just writing the function and here's my answer. Somebody can see what you plugged in and what you got out a lot easier. So let's work with that function notation. We have a couple of examples here. Number 1 says, given f of x equals 5x minus 3, find f of negative 3. That negative 3 is going to get plugged in for x in the function. And I'm going to use that function notation. F of negative 3 equals 5 times negative 3. I'm replacing x with negative 3. And then I'm going to finish evaluating it. 5 times negative 3 is negative 15. Minus 3 gives me negative 18. So f of negative 3 equals negative 18. When I plugged in negative 3, the function equals negative 18. That's function notation. Number 2, given g of x, works the same way, it's just named a different letter. G of x equals negative x plus 4. Find g of negative 4. G of negative 4, we're replacing negative 4 with x in the function. Be careful here, there's a negative in our function, and we're plugging in a negative. So now my function is going to look like positive 4 plus 4. Those two negatives right there made a positive. So g of negative 4 equals 8. When I plug in negative 4 into the function, it equaled 8. Number 3, f of x equals negative x squared minus 9x. Find f of negative 2. We're plugging in negative 2 in place of x. There's 2 of them, and we've got to be super careful. We've got a negative, and we are squaring our x value. We are only squaring the x, not the negative. I want to be sure to show you that example here. Let's simplify this. We've got a negative from our function. Negative 2 squared is a positive 4. And then negative 9 times negative 2 makes positive 18. If you're really careful, you can type most of this in your calculator. Negative 4 plus 18 would be positive 14. So f of negative 2 equals 14. Number 4, given f of x equals 2x squared minus 5x minus 20, find f of negative 9. Again, we've got two x's here. I've got 2 times my x is getting squared. Negative 9 is getting squared. Only negative 9. That exponent is only stuck to that x. Minus 5 times negative 9 and minus 20. So f of negative 9, as I multiply and clean all this up, we've got 2 times negative 9 gets squared. I'm just doing order of operations. So negative 9 squared is 81. Negative 5 times negative 9 is positive 45. And we have minus 20. Simplify some more. Let's see. 2 times 81 is 162. And then 162 plus 45 minus 20, simplifying all of that gives us 187. F of negative 9 equaled 187. I'm going to put stars next to 5 and 6 because they are different. They are going to be different sections on your Delta Math. It says given g of x equals 2x plus 1, solve for x. What was x? What was the input when g of x equaled 7, when the output is 7? So let me show it this way. I'm going to write the problem. We are replacing g of x with 7. The final answer, the output, was 7. You see that? So now we're just going to solve this equation. We're looking for x, what the x value was. So I'm going to solve, and x equals 3. Number 6, given h of x equals negative x plus 4, solve for x when h of x equaled 4. Writing our problem, writing the function there, I'm going to replace h of x with 4. That's my output, and I'm going to look for the input. So I'm solving for x. Subtract 4 from both sides. Yes, it gives me 0. It's weird, but it's okay. This is a negative 1 coefficient. Dividing both sides by negative 1 is still 0. X, when x is 0, h of x in this problem, number 6, equaled 4. Let me show it this way. F of 0, when I plug in 0, the function is equal to 4. Now let's look at the graph here. It says the graph of y equals f of x, some function, is shown below. According to the graph, what is f of 4? Now remember, that would be like writing f of x. So I'm asking, where is x equal to 4? So on my x-axis, 4, what point? So I'm going to look up and I'm going to look down. Where do I have a point? Right there. A is that answer there. That ordered pair was 4, negative 6, but it is point A. On number 8, what is f of negative 6? On the x-axis, I'm going to go to negative 6 and look up and look down to find any point from this function. And we have point B, which was negative 6, negative 3, but it is point B. Number 9, what is f of 0? On the x-axis, this is 0. So look up and look down and find a point from our function. This point was 0, 4, point C. And number 10, what was f of 1? Go to 1 on your x-axis and find the point. That's D. That was at 1, negative 2. Our last two examples are very similar to what we just did. We're going to use the graph to find f of negative 3, or go and find where x is equal to negative 3 on the x-axis. This would be negative 3. So you want to travel up to meet your graph and find that point. That ordered pair is negative 3, 5. So f of negative 3 equals your y value. What was your y value? 5. And number 12, find the value of f of 7. Go where x is equal to 7. This would be 7. Travel up to meet your graph. We have a point there, 7, 4. So f of 7, the y value, the output was 4. So those are some different problems using function notation. Mostly we can use function notation to help us distinguish between different functions. We can name them f of x, g of x, h of x, and then it really helps us with our organization and communicating, hey, this is what I plugged in and this was what I got out, by showing that function notation like f of 3 equaled 5. Somebody can look at that and go, oh, they plugged in 3 and the answer was 5, instead of having to search through all your work and things like that. We can also use it with graphs, whether it's points or whether it is continuous graphs like on number 11 or 12. I hope that helps, guys, with function notation. Practice that on Delta Math, and I'll see you in class.